Good day, everyone. Um, okay. Yeah. Good morning, everyone. I believe you can all hear me. Okay. All right. So today we want to conclude the remaining part of our chapter 4. And we're going to be beginning our discussion today with the topic energy in simple harmonic motion. Last class, we were able to discuss some terminologies used to describe oscillation as it relates to simple harmonic motion. We looked at frequency and also the restoring force in relation to simple harmonic motion as well. And we quickly introduced the pendulum. And today we want to take it further and also look at applications of the concept of simple pendulum to physical phenomena. Okay. So to begin, we're looking at the energy in simple harmonic motion. We established in our last class that simple harmonic motion are motions, special kind of motions that are typified with the back and forth oscillation. And they are also described in relation to equilibrium position. So we're able to establish the maximum displacement, which we call the amplitude. Okay. So looking at the subject energy in simple harmonic motion, we know that we have the kinetic and potential energy dominant in the process or in the simple harmonic motion. We can see that the potential energy transforms to kinetic energy and then transforms to potential at different instances. So what is actually happening is simply energy transformation on the spring. For example, if simple harmonic motion is the description of the spring like we have it here, we can see a kind of energy transformation going from potential to kinetic, kinetic to potential like that until we have the full circle describing this motion. Okay, so we have in the figure A here, the figure A shows us the energy transformation for the mass on a spring. We see at this instant we have the let's say the maximum displacement to the left, the negative, and then to the right, the positive, and then we'll have the zero position here. So we have several positions showing the object on this spring at different instants at the motion. But what we want to emphasize here is that at the start, when we say this start, the maximum amplitude here, to the maximum amplitude on the positive side, we have purely potential energy. So before the spring is stretched, to the point where the spring or the mass on the spring ends, that's they have full stretch as shown in this figure. The beginning of the stretch, as the stretch progresses upward, this is the start, and then the stretch is progressing upward. So you will have the end. So at the beginning and the end, we have purely potential energy. Then in transit, while the spring is in motion with the mass, we have purely kinetic energy. We know kinetic energy is the energy of objects in motion, while potential for objects at rest. So before it starts to be at rest, and then when it gets to the end, before it goes back, it is also at rest position. So if we make a plot of this position graph, of the position graph for potential energy and kinetic energy, we will have what we have in figure B here. So we'll have the range for the oscillation from 0 to positive, then to negative in terms of amplitude, okay? So we have the green line representing the kinetic energy, while the blue line representing the potential energy. And this is the energy for the system. Energy for the system is simply the sum of potential and kinetic energy, right? So for the motion of kinetic energy at the start, that is the maximum displacement of amplitude on the negative side, we see at that point the kinetic energy also, the potential energy is on this side. We see the curve of the kinetic energy being inverse of what the potential energy is, the curve of potential and then that of kinetic, okay? So we have the sum of both at the top here as the red line. So we see the energy being converted from rest, it goes into motion, gets this 0 point for kinetic energy, and then for potential here. At the midpoint here, the mass is still transiting because that is where we record the maximum velocity from the midpoint. So the energy in transit is purely kinetic energy, and that is represented with this green line. Okay. So we can see that energy is transformed from one to the potential and kinetic energy are transformed from one to another. And at the end, we'll have the total energy of the system to be the sum of potential and kinetic energy. Now we see the elastic potential energy, which is the potential energy of that spring, when it was stretched at a distance x from its equilibrium position. That is, we mean when it was stretched, this is equilibrium position. Either it compresses or it stretches out, okay? So when it was stretched, we have the maximum, if it's stretched to the left, maximum displacement, which is the amplitude to the left, negative, and to the right, positive. So when it was stretched that distance, we have that the potential energy is given by U equal to half k s squared. S standing for the distance of stretch, and you know what k is, spring constant. Okay, but because the analogy we are looking at here, or the image we are looking at here, the mass is moving on a frictionless surface, so we don't have any loss of energy to thermal energy. We don't have any loss of energy in terms of thermal energy, so the total energy of the system is conserved. Therefore, we'll have that the total energy of the system, which we've already seen earlier, to be the sum of potential and kinetic, given as, this is the equation for kinetic energy, you know that, half mv squared, and the half kx squared for potential, which will equate to 0 or constant. Okay, so we'll have kinetic plus potential being equal to 0, or you just put a constant there. So from our figure B, as we've seen above, we can only have the maximum displacement to be either positive amplitude or negative amplitude. And at the velocity being equal to 0 when it's at rest, the energy is purely potential, which we've already said the beginning and the end. The object tends to come to rest before they make the next motion. So at that stage where we have the maximum displacement, either plus or negative A, we can actually use A, which is the amplitude, because we understand that displacement is amplitude in this case. So we express that potential energy at the maximum potential energy, half Ka squared all right, is given as half Ka squared. It's the same thing as half Ks squared that we saw before, S being the displacement, which is the amplitude. Okay, so even when it is negative, when the square takes care of that. So at maximum elastic potential energy, we have the equation for potential energy to be given as U max half Ka squared. Okay, so the same goes for the velocity or the kinetic energy at maximum velocity. That's what we have also as V mass being equal to K mass, potential energy maximum being equal to half M V mass squared. Okay, so we have the same thing, but this is describing the scenario where the potential energy is at maximum and the kinetic energy is at maximum as well. Okay, so we should take note of this formula for potential energy here. Elastic potential energy in simple harmonic motion is given as half K S squared, which at maximum is given as U max being equal to half K A squared. So we'll advance further to look at how do we find the frequency for simple harmonic motion. We've seen the energy, we know what our E is, which is equal to E plus KU. We know what K is and we know what U is. So now we want to look at how we find the frequency for simple harmonic motion. Now we also go from the known to the unknown. We have here that the equation for the kinetic energy and potential energy, which we saw earlier, is equal to constant. And we can say it's equal to 0. So if K plus U is equal to 0, it means that at a point, K was equal to U. All right, that is why it is 0 when you add them together. Okay, so the total energy in the system we already know does not change. We can only see it transform. Therefore, we'll have the maximum potential energy equation to be given as the equating the maximum, look at the word maximum, equating K max to U max. So we have half mv mass squared being equal to U mass. This is our maximum energy equation. Okay, so from the energy equation, we'll be able to derive our frequency. So solving this equation, I'm making this one the subject of formula. If you make V the subject of formula here, we'll end up with V mass being equal to root K over MA. The root covers only K over M, does not cover the A, take note. I encourage us to work it out to see how we arrive at this. But what we just did was to make this the subject of formula, V mass, subject of formula in the equation. So we'll have V mass being equal to root KMA. Now, if our V mass is equal to root KMA, and we have seen in our earlier class, the definition of frequency and the maximum velocity for, actually we saw this for circular motion, and we already established that circular motion has link with kinetic, with simple harmonic motion in our last class when we looked at the motion of a ball moving in a circular motion. When it was projected on a screen, it gave us a simple harmonic motion, which is the back and forth motion of that ball placed on the turntable. If you remember the last experiment we looked at in our last class. Okay, so there we established that V mass is equal to 2 pi f A. You already know the definition of the parameters. What A is the amplitude there, and F is the frequency. So if we equate these two, we'll now have root K over MA being equal to 2 pi FA. So we'll make F the subject of formula here. A can go. So if you make F the subject of formula, we'll have F to be equal to half 2 pi root Km. So, and we know the relationship that exists between frequency and period. So if we have the frequency expression to be this, the inverse is simply the period. That is why we'll have it this way. So this is the frequency and the period expressions for simple harmonic motion. For the mass M on a spring with constant K. Okay, so we should also add that to our formula archives, the frequency and the period for simple harmonic motion. So the explanation of that equation is simply the fact that the frequency of the mass on the spring actually depends on the spring constant and the mass, the root of the spring constant and the mass. So we have when the spring is stiffer, we have high frequency, and when it's soft, we have low frequency. So let's quickly take one example to explain some of those concepts on the spring and the energy processes in it. A spring has an unstretched length of 10 cm. A 25-gram mass is hung from the spring, stretching it to a length of 15 cm. If the mass is pulled down and released so that it oscillates, when you pull down the spring, you release it so that it oscillates, what will be the frequency of the oscillation? Okay, so we'll try to make a pictorial representation of what we've just read. We have the original mass of the spring to be 10. When we hung the 25-gram weight, it stretches by additional 5 cm, making the total stretch to be 15. All right, so this is typically the picture of what the question is saying. If you now happen to pull this and make it such that it will bounce up and down, that's front and back like that, the question now is, what will be the frequency of the oscillation, that kind of bounce? Okay, so we'll begin our equation for solving our equation from, we know where we got this, we got it from, so F is equal to MA, but in this case, we're referring to G because of the presence of the weight of which is the gravitational pull on that object. We'll have mg equal to k change in L. Okay, so if we make k the subject of formula so that we can get the spring constant, that is the force on that spring, we now have divide both sides by this. We'll have mg over change in L. Mass in gram converted to kilogram gave us 0.25, and then G 9.8, and we'll have our change in length, which is actually 5 cm. And when we took that to meters, we have 0.05 meters, and we solved for K. So now that we have our K, we can actually go ahead to look for frequency using the equation we just derived for frequency, which is 1 over 2 pi root K over M. So our mass is given, K is known now, we substitute straight into the formula, and then we'll have the frequency to be 2.2 hertz. So the frequency 2.2 hertz is the 2.2 oscillation per second that system needs. Okay, so I'd like you to do this assignment. This is just the one question we'll solve, and the due date is 20th. I will be turning it in on Moodle. I'll create the platform for that over the weekend so we can submit as at when due. All right, so let's proceed to another part of interesting side on the discourse of simple harmonic motion and oscillation. We've looked at the pendulum before, but what we're looking at now is the pendulum motion. Okay, we looked at the pendulum in our last class, and we're able to establish that the oscillation of a pendulum is actually about the equilibrium position. Like we see, we have the displacement range, the negative and positive side. And then we also describe or discuss some terms where we saw that we represented theta here, and we call that the displacement, and then we solved. I want you to recall, we solved this in our last class where we mentioned it, where the displacement, which is theta, angle of displacement, is actually the length displacement arc over the length of the thread or the pendulum. Okay, so for pendulum motion, where it differs from what we saw last time, is that we are describing the motion that is following the back and forth oscillation about the equilibrium position. So where we have parameters such as L, which is the length of the thread to the pendulum, we have the arc length, and we'll have theta there, which is simply the displacement, angle of displacement. Let's call it angle of displacement. Okay, so we have that in this figure, the parameters already outlined. The net force acting here actually will make us see the direction of that motion, because acceleration will be towards the direction of the net force. Okay, so we'll have the restoring force being proportional to, that's the first, which is net force that is pulling it back to the equilibrium position, is proportional to the displacement. It can only go further to the displacement position and goes back. Okay, so we have the net force given to us as, we are using minus because we can see the net force is going back to the minus direction. So minus mg over ls. Okay, so this equation is not new, we've seen it before. So if you recall that when we described oscillation in our last class, we said the displacement x as regards to time is given as a cos 2 pi f, and then for this also we have it to be displacement. This is displacement in the description of length, arc of the length, displacement in reference to the angle of displacement. Okay, so we see that with the arc we describe with amplitude, but with this we describe with the angle. Okay, so we already have our frequency for simple harmonic motion established as k being, that's 2 pi, we have k here and then we have m here. But for simple harmonic motion, that equation, the frequency and the displacement of a pendulum with length L, we use a different expression. Instead of the k and the m here, we are using the length and then the gravity. Okay, so how this is derived will spell us that. So also you should take note that the frequency for pendulum motion is given as half pi or half 2 pi root g over L. Okay, and the inverse gives you the period as well. So this is the period and frequency for pendulum motion. All right, so I'm just explaining the implication of that equation, that the stronger gravity will increase the restoring force. The stronger gravitational pull on an object, the restoring force tends to increase, and that depends also on the length of the pendulum itself, and yeah, the length is like the length of the rope. That's what we mean by the length of the pendulum itself. So when you're asked any question, there are always hints in the question on exactly the parameter that you've been asked to look for. So you just pick any equation that applies. As usual, we'll have a formula sheet, but you should also practice with them so that you get used to the formula to pick from the formula sheet. Let's see an example. A grandfather clock is designed so that one swing of the pendulum is either in either direction takes 1 second. So what is the length of the pendulum? All right. One swing in either direction takes 1 second. That means the total period is 1 plus 1. One swing in one direction is 1 second. 1 plus 1 will give you 2. That is the full period for that cycle. So we are asked to find the length of the pendulum. So we simply, since we know the period, we simply substitute into the formula. So formula for period is simply 1 over f, which is 2 pi. Remember what f was, it's inverse right now. So 2 pi L over G. L is known, is what we are unknown. That's what we are looking for. So we use G, which is 9.8. So if we make L the subject of the formula here, we'll have this equation. L equal to G into period over 2 pi squared. So G, we substitute directly, 9.8, period is 2 pi all squared, and we'll have 0.993 meters. That is the length of that pendulum swing or pendulum rope. Permit me to use the word rope. But once we say pendulum, you already know it's a ball tied to a thread or a rope. So let's look at physical pendulum and locomotion. In our last class, we mentioned that we'll be looking at this, but we are not going to dwell on it. We just want to give us an expression because we will have some problems to solve using this expression. We know that simple harmonic motion always take a particular kind of rhythm in its motion. And if we bring that to locomotion, that is when you walk, you see that your foot or the steps you take follows a particular kind of rhythm that can actually be linked to the same motion of the simple harmonic motion. In this case, the pendulum motion exactly. That is the repetition, a back and forth movement repetition. So we see an example before us, the simple pendulum motion picture and the physical pendulum picture. Like when you take full step, that's one of the examples of the physical pendulum. We'll have objects that we keep or store such that they take the physical pendulum motion shape. We can compare them exactly to the simple pendulum. And where they differ is in their calculation, instead of us to just use frequency equal to G over L, we'll be bringing in definitions such as the mass, the inertia, and the distance. Okay. So this is the D. Remember when we looked at center of gravity, distance that will make them to tilt or not, that is come back or fall away, the distance that will bring about a restoring force. So we have frequency for, take note, frequency, we have seen, this is the third frequency equation we'll be seeing today. This one is for pendulum and locomotion. We have to put in the factor mass and moment of inertia. So this is the frequency representation for physical pendulum of mass M, moment of inertia I, with the center of gravity D from the pivots. Okay, so let's take one example. A student in a biomechanics lab measures the length of his leg from hip to heel to be 0.9 meters. What is the frequency of the pendulum? What's the frequency of the pendulum motion of the student's leg? If the student is walking, what will be the frequency? Okay. Also, what is the period? So we are looking for both frequency and the period. So because they specified here, it's the motion, pendulum motion, but for the leg. So you know you have to put in or use the equation of pendulum motion for the physical pendulum, not the simple pendulum itself. Okay, so applying that equation directly and substituting the information we have from the question, we said that the moment of inertia, which is the pivot about the end, is giving us 1/3 ml squared. So the center of gravity of a uniform leg in the mid point is such that the length will be L/2. So that's why we have the D here being replaced as L/2 in the substitution. And then the moment of inertia is given in the hint to be 1/3 ml. So substituting this and solving it out, we'll have 1/2 pi, 3g, and 2/2l. So we have all our parameters given. We are looking for frequency. Substituting directly, we solve to get 0.64, and we take the inverse of this as the equation of frequency says to get the period. Okay, so that's how I apply that to solving problems with locomotion. As you take your step, we can actually calculate length and other information about your motion. So let's quickly look at another concept called damped oscillation. Now, when we say damped oscillation, we simply mean or refer to oscillation that runs down and then stop. If you see from the diagram here, you can see the oscillation running up and down, then fading away. This process is what we call the damped oscillation, oscillation that runs down and stop or fades away. Okay, so we have in figure A, a typical oscillation such that fade away that we describe as damped oscillation. Initially, there's a large difference in the height of the successive peak. You can see it's obvious, the difference in the height. By the time it will be returning, it did not get to that former height. It's dying out until it fades away. This is what we call damp. Then let's not just do, because it is cumbersome to always have to look for the distance between the first peak, second peak, third peak, when we have system already established to help us get that out. So in solving this kind of problem, sometimes either will give you details as far as the distance between the amplitude displacement, the ones that are fading away, and we'll give you more details if you're asked to do something like this. Okay, so let's now imagine we draw a straight line across the damping oscillation. We'll see the expression for that straight line drawn now to be the displacement maximum as a function of time, which is equal to the amplitude, the exponential minus t over tau. Tau stands for the time constant, okay? So we see this expression called the exponential decay. So we always have the exponential decay for damped oscillation given as t, maximum displacement as a function of time being equal to amplitude exponential t over tau. Okay. So if at a time t is equal to tau, the expression for the time constant here we transform into this. All right. So we have a raised to the power minus 1 being equal to a over e approximately 0.37 a. Okay, that is the approximate maximum displacement we can get for damp oscillation. So let's take an example. A pendulum of a grandpa clock has a period of 1 second. If the clock's driving spring is allowed to run down, damping due to friction will cause the pendulum to slow to a stop. So if the time constant for this, remember what time constant is, tau, right? If the time constant for this decay is 300 seconds, how long will it take for the pendulum to swing to be the question is, how long will it take for the pendulum swing to be reduced to half its initial amplitude? Now, this simply gives you an idea that this, because the amplitude is reducing as it's swinging, then it's a problem with the damp. Then you come to the damp equation to pick one that applies to the problem. The question said, how long will it take to go to half of that swing? So first we wrote out the expression of the maximum displacement, and then we don't have information about the amplitude, so we have other information as it relates to the expression of this decay, exponential decay in terms of the angle of displacement. So we have θ1 being the initial angle of displacement, and then time, t. So putting that into this equation, we have this θ max to be equal to half theta. Now we got this half theta because that's what is given, half the amplitude. So we just assume that amplitude is half the value that was given. Okay. So equating this angle of initial angle will cancel out. So once they cancel out, we'll be left with the key part of the equation, which is exponential minus tau, minus t over tau equals to half. So solving that out, we took the ln to eliminate the exponential, and then we have the final expression to be minus ln 2. So if you press hit on the minus ln 2 on your calculator, you have a value. Multiply that because it is specified that the time constant is 300 seconds. So we just multiply that with the information of the t we got to get 208 seconds, which is the time it took for them to get to half of the amplitude. Okay. So converting this to minutes, that's all, have 3.5 minutes. All right, so let's look at the concluding part of our lecture for today, which is the driven oscillation and resonance. Now, we already know what oscillation is. We always remember this, the back and forth motion, and then we have additional descriptions to it. But when it comes to driven oscillation, we're actually referring to an oscillation with the external force induced to bring about that motion. Okay, so driven oscillation is an oscillation subject to the periodic external force. It's either the external force is the one that initiated it, or it's in the system before it comes in. But what we want to establish here is that driven oscillation is actually induced from the external. Okay, so we have examples such as the jiggling of your back, front, and back, and then we have other interesting examples as well. But we want to establish that once it is driven from the outside, the force inducing the motion is an external force, then we can say the oscillation is actually driven. Okay. So how does this relate to resonance? We will also see detailedly as we progress. Because we make mention of driven oscillation, and we have made mention of periodic external forces, we want to quickly establish that for resonance, if you have, for example, the force, or let's use we have frequency for external force. We also have what we call the natural frequency of a system. That's the frequency before it's altered. That frequency is F naught. So when F naught is equal to F net, resonance occur at that point where the net force is equal to the natural force. So resonance occur if the system is driven with the frequency of the driven frequency or external force, and it matches the natural frequency. This may produce a large amplitude of the oscillation. So that is how we know that that happens. We suddenly see a high peak, and that is what you have here. A position where the natural frequency is equal to the driven frequency. And so we call this F naught the resonance frequency or natural frequency, but we'll call the Fx, okay, the frequency for external force, the external force frequency. And what you have noticed, this resonance occurs when F naught is equal to F net. Okay. So to buttress that, we'll have the description here. Let's assume that a system has a natural frequency of 2 Hz. Okay. And then you make a plot of the amplitude against the external force. All right. If we make that plot, we will notice that a time comes where there will be a high peak. And this high peak point, we have already said that it occurs when the F external is equal to the natural frequency. And at this point, the oscillation is at maximum amplitude. Okay. And then the oscillation here is very small. At small amplitude, you can increase or reduce this height. Okay. Now, if we look at this, the B part of this diagram, we'll see the response curve as it becomes longer and taller. What happened? Something must have altered that. Let's see. So the narrower ones are the damped ones. Remember what we said about damping, slowly reducing amplitude until it fades away. Okay, so look at this graph. We have three different motions in one. One with F equals to 2, yeah, F equals to 2s, and then we'll have the other three with different, entirely different damping factor. Okay, so damping actually made the peak to go longer, all right, and narrower as well. Okay, so we see plotting Fnet and amplitude as well are different. Also keeping in mind the natural frequency, but we're plotting at different tau at 2 tau, that's 2 times period, 20 times period, and 50 times period. We see that the one with the largest is the one that has the highest peak. So the slightly damped system has a very tall and very narrow peak. But when the system is significantly or blunt or not damped, the response are usually flat or very wide. Okay. So another place where resonance is applied in our body as human is in the hearing. Okay. So we see that resonance is a system. Resonance in a system means that certain frequencies produce a large response, other do not. If you look at that graph, it is emphasizing that at this point, frequency here will give you very long, right, peak, but others did not act as if there's anything going on. Okay, so we see that resonance actually in a system means that certain frequencies, note that word, produce large response, which is the peak that you see, while others do not. So it is easy to see the peak and not confuse it for another thing. So the phenomena of resonance is responsible for the frequency discrimination of the ear. If you play too high pitched song, you can hear things like the pitch is high, reduce your volume and all that. Okay, all these processes of hearing sound, controlling, is actually the study of the ear structure that bring about that. Starting from the routine biology that we know that the ear and the structures in it helps us to filter different pitch. Okay, and that is what resonance helps us to do as well, to discriminate or differentiate between pitch. Now, this is the figure or structure of the ear, inner structure of the ear. We have the common parts, which is the eardrum and all that. Let's assume that this coily part is stretched out to look something like this. Okay, so now somebody will ask, did it yield a better result if it's stretched out, or does it matter? Let's see. When you stretch it out, fine, you don't have the the space. Yeah, you need more space. But we're just going to look at it stretched out just to understand the principle behind uh, the resonance and the hearing. Okay. So we imagine the spiral sound. Imagine the spiral part of the ear that helps control sound stretch to the figure you see here now, such that also the basilar membrane is separate. Now, this will help us differentiate. What it normally do is to help differentiate or separate the several frequencies for which sound was given. We will also see this when we start studying or looking at sound as well. We'll make mention of this, but we just want to establish that the ear, the structure, they all help us to filter different pitch or pitch in sound that we hear. Okay. Mm, 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 mm. Okay, so we end our lecture here. By next week, we should be proceeding to chapter 15. And if you have any question about the lecture for today as well, you can send me an email and I'll be replying you as well. The assignment is inside. I said I'll create the assignment page where we can have it handed in online. All right. And we'll have several questions for you to practice with. As usual, attempt what you can. And these are just summaries of all that I've learned about oscillation. And we hope that we can solve almost any problem on oscillation. All right. Okay. I'll be expecting the feedback from you to be sure you actually went through this class. All right. Thank you so much. Have a great day.